Today we're going to be doing a design exploration of the Simbotics 2019 robot. We'll look at some of how the robot actually competed, and then we'll go and dig through the actual CAD model and look at a lot of the details that make this robot work. So this robot was Simbot Snowstorm. Competed in the 2019 FRC game Destination Deep Space. They were one of the best robots in Ontario, one of the best robots in the world, with a lot of relatively standard features for this game. They kind of packaged everything they needed to in the robot well. But there's a lot of little details when you start digging into it that make the robot really interesting. So first we can see some of the pictures and kind of see the overall kind of scheme of the robot. We have the drivetrain, the two different intakes. So this game had a cargo ball and a hatch panel, so you had to be able to intake both of them. So they had there's these little flippers here for the hatch, and the intake was able to grab the cargo ball. Then they had the elevator to lift it up to different positions. And on the back here, they had their level 3 climber. This back mechanism was able to lift their robot and set it up on top of the level 3 platform. So we're going to look at kind of the progression real fast, and we'll go through these matches pretty quickly. But we have their very first match of the season. So this is before they were able to kind of be good yet. This is the very first time they played. Actually, let's back up. So this is their auto. Or Sandstorm coming out in their very first match. Here's them right here. So they're able to get that first panel, and then they basically just spin in a circle in their first match. So we don't know if that was intentional or a problem, but it didn't affect them really in any way. They got that hatch done. And then as Sandstorm ends, they start trying to collect some more hatches. And again, this is their very first match, so you're expecting to have some bugs to work out. This is kind of part of why we're seeing it, is how to see how well teams get as the season goes on. I mean, even we're not going to watch the last match of even this event, but you could go back and watch it, and you could see how much better they were just at that point. So now they're able to do some cargo from the floor, and they're getting pretty solid there. Interesting to see they didn't put hatch panels on these sections of the rocket, so they had those cargo balls fall out, which are the two they were able to put there. So there's some sort of strategy things that they did kind of early on that they probably don't do in the future, but it kind of just depends on how fast they think they could be. So I think they thought those balls would help them in reducing travel time. They didn't have to drive all the way back to get a cargo ball from somewhere. Now they're up to the third level of the rocket. So part of the goals of this game was to get a complete rocket. So you had to have all 6 hatch panels and all 6 cargo, and you'd also get a ranking point. So that's one of the things they're attempting, while also attempting to win the match. Yeah, there's some timing on like when human players bounce the balls and things. There's a lot of that gets better in the late season. They actually do come out and fill the rocket, I believe. Yeah, so they get 6 and 6, and then they get their level 3 climb as well. So from very early on, they were performing at a high level. Yeah, so they end up winning that match, getting all 4 ranking points at the very beginning. All right, so going forward, we can skip all the way to their champs performance. So this is the final match at, hit the wrong button. This is the final match at the championship. Here they are, there's a top view of their robot. So their Sandstorm got a little bit more complicated. They're putting a hatch on that center spot, going to get a second one and hatching it there as well, or trying to. So they get that failed hatch, but they hold on to it, and then they have a defender on them basically immediately trying to prevent them from scoring. So the defender has them on that side of the field. They're having trouble getting back across. This is definitely not where they want to be at this point in the match, right? They're trying to get back over and continue scoring. 2056 is their alliance partner here, doing totally fine, getting the job done. But now they have no hatches on this rocket, and they have to hatch the entire thing under defense, which was a hard challenge this year. There wasn't a lot of teams who could do this extremely well. Because eventually it just takes time. Like even if they do it, even if they do it well, it just takes time to get all of those hatches on the rocket. One of the things you can see for people who haven't watched a bunch of matches before, there are every once in a while you'll see a ref down here waving his arms. That's the pin count. So you're only allowed to pin a robot for a certain amount of time. Most games it's like 5 seconds. And so if they start pinning, the other robot eventually has to back up before that 5 seconds, or they get a penalty. You can see it right there. He's waving his hands. You have to back up a full 6 feet before the pin count is cleared. So here, then they're eventually going to try to do a double climb with their partner robot after only putting in the 4 game pieces on this rocket and this single hatch, and they also knock over their partner when they go to climb. So just all together, not great, and this was how they exit the championship event. Turning that around, by the time IRI came around, they ended up playing with their the same partner again. They played with 2056. They're on the far side of the field, so it's a little harder to see. For Sandstorm, they do get the 2 hatches that they go to place on there. 2056 runs a separate Sandstorm that actually pushes the panels to the rocket, and then they flip places. And this is one of the biggest things that happens in this match. So instead of having 1114 with no hatches on the rocket they're working on, they have 2 hatches ready to go. That forces the defender to basically play on 2056 and lets 1114 just kind of do their the same job that they've been doing since that very first match of the season, where if you just give them an empty rocket, they're able to fill it up nice and fast. And so all of their movements have gotten a lot cleaner and faster from that very first match, right? The amount of time it takes for them to go get a hatch and back is so much shorter than it was in that first match. Kind of the sequence of where the next ball is, where's the next object to place. They have all of that down a lot more complete and ready to go. They'll still make a few mistakes right there. They had to like kind of clear out their elevator, get everything reset, but it didn't cost them a lot of time. Even that, right? This is final 2 of IRI. They're about to win the IRI championship if they win this match. It's a lot of pressure. So a little thing like that where the ball came out, that's something that can happen. And then we do see this flip. Now you have Strike Force playing D on them now. Yeah, and they still drop some balls. Like it's still not perfect here. Like towards the end of the match, it gets a lot less clean than it was early on. few seconds left, they're able to very late kind of get that jump up to the top platform, which is what their whole robot was designed around. Like, we'll look at that mechanism a lot. Their mechanism was designed to be an incredibly fast level 3 climb. They didn't want to have to wait on anything. They wanted to get back and up on that platform in a very few amount of seconds. And then at the end, because of the defense that their partner was able to do and the hatchet and the scoring that they were able to do on their side, they get the win and took the IRI championship. All right, so going forward, we have one more. Let's see if we can actually get out here. So we'll let them explain parts of the robot, because I don't need to explain things that they've already explained. And then we're going to dig into the details of the CAD and kind of some parts of the robot they don't go over in like the overview video that they do here.
Hey, this is Mike with the FRC Top 25, and first updates now. We're here with Hall of Fame team 1114 Simbotics here in the Curie division at the 2019 Detroit Championships. And guys, we're here with Evan, Cole, and Nick. This is kind of really special because back in 2013, 1114 was the first team we ever did a behind the bumpers with. So it's really exciting and an honor to be back. So Nick, we're going to start with you. We're going to start with kind of walk us through your intake here on your robot.
Yeah, so this is our intake. We did a lot of focus on just like quick, go and get it. So we have the roller here. We can start off with that. So we use 4 Mecanum wheels and an Omni wheel. So the Mecanums help us center it. So we have these bars here that like, at our first event, we didn't have the bars, and then the ball would just fly past it. So for our second event, we added these bars. So now if Evan does it, it'll just immediately suck it into the robot. And if he outtakes it, it's just back and ready to go again. So that with the panel intake, our main idea with the whole robot was just to keep it as simple as possible and as fast as possible. So if he brings the fingers out, Evan, bring the fingers out. Just see how almost instant it grabs the panel. So if he outtakes it, it does that from the quick release valves on here. And then if he does it again, we make sure that no matter what, this isn't coming off. Even if someone like hits us, and we just keep it as sturdy as possible. So now we can probably turn it around and show off the climber.
Should we like take it off? Oh, that's fine. So I'm just going to talk a little bit about our climber. A big focus of ours this year was to climb as fast as possible so we could continue doing cycles for as long as we possibly could, scoring as many points, and then getting on with like the last 5 seconds. So as you can see here, the climber is run by 4 775 pros, and then it's geared to about, I think, 439 to 1. And then that drives this little leg. And then as the leg rotates downwards, the chain bar mechanism acts as sort of like a virtual 4-bar and keeps the entire foot and center column perfectly parallel with the ground. So we can rotate all the way around onto HAB level 3 in about 2 seconds, including like the entire lifting the leg sequence. So then with the leg being all the way retracted, we can also like spin out of the way and get out of the way for other teams to possibly double climb with us. Yeah, we can climb with under 2 seconds, which has been really helpful for us this season. We've had a few matches where we were about at the rocket with about 5 seconds left. We got back and climbed, which has been really helpful. We've only missed the HAB RP, I think, 2 times, and one of them was because our partners were dead. But, you know, stuff happens, so that was one of our goals this year, to make sure we always get that HAB RP.
So I guess as far as programming goes, one of the main things this year that was a bit of a jump for us was that the main sensor on this robot is all just on the vision from the camera. So for picking up panels, we use the camera to figure out how far away we need to be. So all of picking up panels is just done with just the press of one button. Evan, the driver, just has to press one button, and that makes the robot drive to the panel, triggers the intake to pick up the panel. And then all that driving and turning is done completely autonomously by taking in the camera to get distance and angle. In addition, for picking up balls, we don't have a sensor or anything on the intake. We just look at the current draw from the motor, or from the Neo on there. So as soon as the current spikes, it just picks up the ball and flips the wrist up. No input from any other sensor required. And then on top of that, we also use the vision to line up when we're going to place panels. So I don't know. Yeah, it's not what I was talking about.
That's
pretty crazy.
That's quite all right. So again, thank you to Cole, Evan, and Nick for your time, and the rest of Simbotics. Ontario provincial champs this year, and doing really well in the Curie division so far. And good luck the rest of the way.
All right. All right, so that's the end of our videos. There may be one other one that we look at in a second. So I was actually able to, I was up in Detroit for them to see them at championship. So I got these are photos that I took of their robot. So when we need to look at some details, we'll come back and look at some of these as well. Let's flip over to the actual CAD model and start looking through how they went about designing their robot. So one of the interesting things about the Simbots robot this season was it was one of the first seasons where they didn't have a sheet metal drivetrain. So if you look back at some of their past robots, most of them are built with kind of a different build mechanism. So this webpage has all of the CAD for most of their previous seasons robots. And most of them had a drivetrain built closer to the way that Spectrum has built drivetrains in the past, which is basically almost entirely sheet metal, where we have a sponsor laser cut and bend the parts for us. In 2019, Simbots did not have a sheet metal drivetrain. They had a drivetrain that was based off of an aluminum tube. This right here, this is a 2x1 aluminum extrusion, which is kind of the standard for most West Coast drives. But they did a little bit different because there's a lot of what they are built around and how they do things. They wanted to keep some of the same features of a sheet metal drivetrain. So their outer wheels aren't actually live axle like a normal West Coast drivetrain would be. And I think we've looked at some robots who do it that way before. And we talked about live axle before. So the wheels here are actually spinning on, the bearings are in the wheel the same way that most of the Spectrum robots work. For all of their wheels, their center wheel, however, is a live axle. So this wheel is powered and the shaft that's spinning on it is powered. So this hex shaft right here is being driven by the gearbox. So we have two motors, and so there's two more on the other side that look exactly like this. This is what's known as an inverted gearbox. So the motors are kind of pointing back towards the wheels in sort of the standard gearbox layout. The motors would be pointing, the back of the motors would be towards the inside of the chassis, but you can build them in this way to save a little bit of space. So the motors actually hang out over this tube right here. So you save that little bit of width. You could also even, if you could design it, you could build it back even further to where the motors were further out, kind of over these sprockets. And they just kind of save room in the middle, because it's possible that this motor might have started hitting some of their internal mechanisms if they were pushed out too far. That's one of the reasons to run this inverted gearbox. The gearbox, just like most of the gearbox in FRC, take the fast spinning motors and make them spin slower and with more torque. Oh, I hit a button I wasn't supposed to. Where am I at? Okay. Let's see if I can get back to where I want to be. All right, there we go. Okay, so yeah, so I believe I don't know if they did I think this is one of the standard West Coast products one, but it could also be a custom one. I'm not sure off the top of my head. Yeah, so this is one of the West Coast products ones. You see the WCP in the part name. So West Coast started selling these, I think about a year. I think in the 2019 season was the first season they were available. And that lets them package that easily. It's commercial off the shelf, so they can buy it very quickly. They don't have to worry about designing their own gearbox. They're able to get the ratio and things they needed to get the drivetrain speed they wanted for the game from something that they could just purchase and make it easier. They use the Vex Versa Blocks, so that's what this part is right here. Maybe there we go. So this Versa Block part is a pretty standard part from Vex that's used in a lot of West Coast product or in a lot of West Coast drives. It lets you put a bearing without having to do like a precise bearing hole inside the tube, so you don't have to mill anything there. And they use one on the other side over here as well, so that again holds the bearing in place. And so that's kind of how they get their first wheel driven. So that hex shaft coming right out of the bottom, this hex shaft here, running the whole length, drives this center wheel. They have 2 sprockets attached to it that are used with chain to run the outer wheels. And kind of the biggest difference here is instead of like a normal West Coast drive, they have this outer flat plate that they're using to hold the outer edge of the shaft. So most West Coast drives are characterized by having a cantilevered shaft where they only have bearings for your drive shaft on one side of the wheel. So this other side is normally completely open in West Coast drives, which makes it very easy to say take the wheel off. So if you need to swap wheels on a West Coast drive, it's normally super simple because you don't have this plate right here. So you just take off whatever is holding this. Sometimes it's a bolt, sometimes it's a snap ring, and you can just slide the wheel off, replace it with another one, and you're good to go. If they need to do a wheel replacement, it would definitely take them quite a bit longer to do, right? I'm not sure exactly what their process would be. It's possible they can slip the shaft, this drive shaft out in one direction or the other, right? If they could push this back, I don't know if it hits, yeah, it runs into something pretty quickly. They have the encoder mount there, so it's probably not coming out that way. So it's likely they're taking this whole plate off if they need to swap that wheel, which may not be too long of an operation. It kind of depends on how fast some of the other things are mounted in here. But they probably didn't do it very often. They have a wheel that's able to have the tread replaced without swapping the wheel. So unless they're damaging this wheel for some reason, they don't have to replace it very often. Looking forward, these blocks right here are actually just pieces of wood. So 1114 is known for this. It's pretty common. So you can see in this photo right here, these are just pieces of wood that basically strengthen the gap between their wheels and that plate and the tube. Wood has a relatively low density, so for its size, it's relatively light and it's very stiff. They also they had to bore a hole through it, it looks like, to be able to get that shaft in, is what it looks like, right? So if they're able to drill a hole all the way through. So if they need to put this hex shaft that runs all the way kind of under between their 2 sides of their elevator, we'll look at that in a little bit. But that's one of those small details that if you don't have and you put everything together, maybe you're able to do it before you put the blocks in or something. But if something has to change or if something gets damaged, now you're looking at taking a bunch of stuff apart, but because they thought ahead and realized, okay, if we need to maintain this, if something does break, we'll have these holes ready to go and we can get the shaft in and out because we already have these ready. So little things like that add up, especially in a season when some things are unpredictable. You can't always tell where a failure is going to be. Designing to make sure you can actually work on the robot is super critical, and that's one of the little kind of design features you can put in. Things like that of how do you get shafts out, how do you get nuts and bolts out, what's the order of operations, how many things have to be removed to be able to fix something. A lot of the thought goes into that when we're designing the full robot. Let's look. So we didn't finish because a lot of it is on the drivetrain. They did some unique things. So coming back to their back wheels, we have some things that not a lot of teams do that they do a little bit differently. So we have this hex shaft here. This is actually a Thunder hex shaft. You have kind of like the little rounded over corners there, which isn't that different than a hex shaft. You could use a regular hex shaft here too. But then they have the bearings in the wheels. So when this wheel turns, this shaft doesn't rotate at all. So this shaft is completely stationary. It's not rotating. It just acts as an axle for the wheel, and the wheel spins on it. And then they build in these features here. So they have these slotted holes on all 5 of these mounting holes, and they do the same thing back here. So it's hard to see the inside of this. Let me make transparent. All right, so there you go. So you can see that there's the 5 bolts here as well. And there are slots for them that are hard to see when that's transparent. All right, yeah, so then those slots exist there. They also milled out the entire feature on this side, so you can get a Allen wrench into here to be able to tighten and loosen these if you need to. And they left enough space here to be able to get a tool in there, right? They didn't mount anything directly next to it because otherwise they wouldn't be able to tighten anything there. Kind of rotated myself around a little bit. The same thing is true for right here. So up at the front, they have the same exact pattern, same holes. Basically just a bolt with a washer, and they can run it inside those slots. This hole right here has to be big enough to be able to put the bolt and washer inside the tube. So that's how they're actually able to place it in. They kind of scoot it in, they push it in from this side, and they're able to bolt it. The other side is just a slot. You can kind of see in where the orange is highlighted there. And so what those are for is that so they can move the wheels forward or backwards to keep their chain tensioned. So chain, as it gets used, will start to stretch during the season. You basically get a all those little links will basically just be able to wear in a little bit, and each one will just change their length ever so slightly. But when you do that over a pretty long run of chain like this from wheel to wheel, you eventually do get a reasonable amount of growth during the season. It's not major. You're not talking like a half inch or anything, but it's enough to where the stain will start being loose. It'll start being inefficient, and you start running the risk of potentially having it skip off the sprocket, which is something you never want to do because then part of your drivetrain just isn't working well. So how they actually can hold it in place, because you just don't want to. They don't want to hold it just on the tension of the bolts here. They actually have threaded spots here for another bolt here and here. I believe it's threaded. It could actually be, there's a pocket here that may allow them to put a nut on the inside of this and the bolt just go through it. I'm not sure which way they end up doing it. It's likely it's threaded, but it doesn't have to be. I know other teams have run threaded ones. You could probably tell based on the size. It's 159, so that's likely the tap for a number 10. It could also be clearance for an 8 if they wanted it to. And yeah, those are both the same. But that's probably tap for a number 10. Then they have more clearance holes. They have a pocketed hole here. So it's not in CAD, but there would be a bolt that you would slide in through this hole. The bolt head would sit on this like inside face of the wall. You'd be able to grab it here. And then as you tighten that bolt, this whole assembly would be drawn back towards the bolt. So you're able to pull this whole wheel, all of these plates and everything, back towards this rail and increase the distance between the center wheel and this back wheel, making that chain tighter. So that's definitely a little bit of a tricky part to make. These are actually, I think these would look like to be the same part. So they would make them twice. We can look at exactly what these parts look like. So they have, so these are probably done on a CNC router or CNC mill. So they can take out the outside profile pretty easily. This inside profile is stepped a little bit. You're bringing down 1/8 of an inch on a 1/4 inch thick piece of material. So this part is what kind of holds in that hex shaft. It gets kind of locked in. You can slide up between there. And then this feature is a little bit trickier though, because you can't do that on a 2D machine, right? If we're cutting something out from a plate that's kind of this big, this has to be done on a second operation to drill into the end profile of this part, which is probably set up on a mill to do that properly. these same bolts, yeah, so these are also tapped to number 10 here, so they're just bolted in through the sides so they can get tightened. You wouldn't want to have a nut on this side or anything. It might start interfering with the chain or sprocket. All right, let's get out of isolate. All right, that's most of the drivetrain. They do 2 traction wheels and on one side and 1 omni wheel. So that means their robot, when they go to spin their robot, instead of it spinning sort of around the center of the robot, it's going to spin basically around the point between these 2 wheels and the center. So you have some point of rotation somewhere up over here-ish, because your front wheels can kind of swing sideways without affecting, without rubbing at all. So these rollers on the Omni wheels allow you to avoid scrub, which is kind of that sideways friction of the wheel when you go to turn. And so just these 4 back wheels will kind of define the center of rotation, and place it somewhere back over here, depending kind of on how the weight's distributed across the wheels and things. You'll get it somewhere back over here. All right, let's see. That's most of the drivetrain. They have to do the same thing up front. So they have this front rail that has those same bolt holes. So they can do the same chain tension mechanism. Again, we see it in that same place. They construct the front of their robot, which is always sometimes interesting, is how do you build a strong frame with this kind of frame gap in it, right? The back rail and the front rail both don't have continuous bars going all the way across. There's this gap right here. And at the front, there's the entire gap for their intake to come into. And so they kind of accomplish that by adding this sort of large orange piece that's highlighted here. So this is connecting this front rail, the side rail, and this cross member that's a little bit further back. It's connecting them all together. It actually goes all the way back and it becomes part of their battery mount, or has a plate for their battery to sit on. And then underneath, they do a similar thing, except they have to do it even differently because they can't cross again. So they cross, they kind of support this whole area by connecting those same 3 plates and then coming back around the other side of the gearbox and connecting this bar to this bar as well, all the way across there. That also gives them a little bit more mounting room. They're able to like mount their compressor there. I don't know if they use the rest of it. So I don't think they have all of their electronics catted. We could go back and look at some of the pictures, but I imagine they use some more of this space for some of the electronics mounting to get everything nice and low in their robot. The other cross member that, yeah, so they can't have any other sort of main cross members. Give me a second. Except for this right here. Even this is cut out a little bit. I'm imagining that was for, at the beginning, they didn't know how long this tube was going to be, right? So you can see that this is that same profile there. So it's possible that this beam is cut this way in CAD. I don't know if it's even cut this way in the real robot. It doesn't appear that there needs to be any reason for this cut, and it would probably be a lot stronger without it. But it's possible early on that their foot needed to be longer for some reason. Who knows? It may have just been some other part of the design that got changed, but it doesn't look like there's a need for it in the CAD that we can see right now. There may be a need that we're just not noticing. And they're actually able to run kind of these second cross member or second long members of their chassis up with a little gap that they build in with the gearbox plate. So we'll look more at this when we go to the climber. But these rails kind of make up part of the chassis rail, and they're able to strengthen the bit that they cut from it with these extra side plates. So this is a single rail right here. We can isolate that and kind of see how they make it. But they have to cut out this section for their climber. And if they didn't if they didn't add in some reinforcement, it's very possible that this would be the weak point. You might start seeing some buckling here. You cut out an entire wall of this tube. So the tube is a lot weaker now because you're missing that whole wall. And a pretty large amount of this flange here too. So this part of it is a lot easier to bend than anywhere else along here. It doesn't necessarily mean it would. It might not ever. They may not need the reinforcement, but going back and reinforcing it definitely helps remove a potential weakness. All right, let's look at the elevator real fast. It's one of the things I know I want to look at before we get too close to the end here. Their elevator, what they were able to do is make a rather simple elevator, nothing too complicated. They have a 2-stage elevator. So you have these external rails on both sides that are stationary. They're mounted to this rail down here. You can kind of see the 4 mounting holes. Then they're also stationarily mounted to this plate and our support arm, support beam coming back down and kind of making this whole thing into a triangle. So it makes it a lot stronger. If you just had this rail coming up, it's pretty easy to kind of push this back and forth. It might want to flex. By adding this support beam and this plate up here, it makes this whole structure a lot stronger. All right, coming into the gearbox itself, they have 2 775 Pro motors. So there's one here and a little gearbox that goes and makes this whole thing spin slower again, just like most of our FRC gearboxes do. We'll get the pinion gear. So that gear that's right on the end of the motor is called a pinion gear again. And it meshes with a second gear here in this first stage of the gearbox. These, you can tell they have kind of smaller teeth. So these are 32 DP gears compared to 20 DP gears. Those are the same. Those are like the main 2 types we use in FRC. The vast majority of the times now we use 20 DP. We won't use 32 DP very rarely at all. And then from there, so you have this first stage of the gearbox, you have a second stage of the gearbox, and then you have the sprocket that's actually driving this chain. The CAD model got a little awkward. This chain would wrap all the way around the bottom here, just like the chain on your bike or any of our other mechanisms we've looked at before. And the chain goes all the way up to the sprocket held in at the top up here. And we have the same exact mechanism mirrored over on the other side. So we have that chain, and it comes down, let me flip around, to the same gearbox over on this other side as well. And there is a connecting shaft going between them. And the reason for that is if you didn't have that connecting shaft and you ran these both independently, it's very possible one of them could get out of position from the other, and you might have like the one side of your elevator is trying to move up faster than the other side, and things just aren't going to move smoothly when you're doing that. You really want them both moving exactly at the same time up and down, so you get nice smooth motion. And by far the best way to do that is to mechanically connect them somewhere. And sometimes that's easier to do at the bottom. Sometimes it's easier to do it at the top. You could have a hex shaft connecting at the top to do that. But at some point you need to be driving both sides of your elevator nice and smoothly. The other option that some teams will do is driving the elevator from a more middle position. So if you drive it closer to the middle and you have a chain running up and down somewhere through the middle, you can kind of be lifting the center of the elevator, and then you don't have to have a second chain. It kind of just depends on the design. They went with 2. They were able to do that and make the whole gearbox mechanisms kind of packaged nicely, nice and small. They didn't need a bigger gearbox that would have had to take in 2 motors. They just duplicated them. And that works well enough. It's also possible that like if something happened to one of these motors, the other one can still drive both sides. You would just be a lot, you just wouldn't have as much torque, but you could probably still lift up and down. So you'd have some redundancy there, which is good. Let's see. So this is driving the first stage of this elevator. So this inside square. So you have, this is the top bar. There's another bar there. There's another bar there. Let me see if I can get the bottom one. And the bottom rail all the way down here. So those 4 right here kind of generate your first stage of your elevator. So this moves up and down directly powered by this chain. So they actually have a little mounting plate right here. Let me get off. All right, so they have this little mounting plate, allows the chain to be bolted to it. And then this is bolted to this rail. so that when you drive the chain, this whole thing rises, and this part of the elevator goes up and down, which is what we want. So to move this second stage, or the carriage, which is often called the carriage, the part that kind of holds the manipulator, the intakes, anything like that, which is these rails right here for them. So they have this rail and these tubes. All of this makes up the carriage. It has the mounting spots for kind of where the intake arms are. All of that part is the carriage assembly. And so to get that moving up and down, if they didn't have any other attachment points, it would just always sit down here, like on this bottom rail. And it wouldn't get very high. You wouldn't be able to score all the way on the third level of the rocket if that was all you had. So what they end up doing is attaching a strap. So that's what this little bolting, either rivet holes, I think these are rivets. So they will rivet in a nylon strap here, and they would rivet in it again somewhere up over the top here. So I believe this roller right here is for that, of the first stage. And that lets them, and that lets the strap kind of roll over the top. And then it also gets mounted to this back bar here as well. So this is a little tricky to look at. We looked at this before when we talked about the Great Elevator like a month or so ago. But basically this is a cascading elevator setup. So as this gets pulled up, this part of the strap has to stay in relation to this. And that sort of does the pulling up of this second stage and gets it closer to the top every time. That's similar to how we've done it in the past as well. We'll just use a second run of chain to do it most of the time. But some sort of strap works too, like they did. Okay, really quickly, looking through their intake assembly, they did want to keep things pretty simple, which is very useful. So they didn't have a motorized wrist, they had a pneumatic wrist. So they have these two pneumatic cylinders here that are able to tip the whole intake assembly out of the robot. So at the start of the match, you wouldn't be allowed to start like this. You have to start inside of your frame perimeter, which is kind of defined by this line here. So at the beginning of the match, these are retracted. So these are pulled back in, and this whole mechanism is tipped up, and sort of this line gets pretty close to parallel, kind of vertical with this line right here. So this whole thing gets flipped up. All of this mechanism gets stored inside. These little fingers are flipped closed, and it allows them to be inside of the rules and inside of a legal starting position. And then when they're ready to actually like grab a hatch or score a hatch or grab a cargo, they'll extend these cylinders and the whole thing tips out to this position and gets their intake out in front of their bumpers. They're able to grab cargo from the entire width of their robot, and they're able to grab a hatch. Even if there's like cargo on the ground in front of them, they're still able to grab the hatch. So that's very beneficial. They do have a little bit of bent sheet metal here. So they didn't have bent sheet metal pretty much anywhere else that we've looked so far. But you do see a small piece right here that has this flange on it. So that adds a little bit of strength here. So it makes it harder to bend. Just like if it was just flat, it's kind of like a piece of paper and you could very easily bend this section. But once you add this flange, it makes it a lot more rigid. The cargo intake itself is a Neo motor with a gear, and then powered. The last stage is a belt drive. So you have these two pulleys here that have a belt between them, connecting them. And there is a hex axle running through the entire length of this intake. So it runs through the entire length, all 5 of these wheels. This is what's called a mechanism intake. So you have these 4 mechanism wheels, sometimes known as vectored intake wheels, which is kind of a joke because we aren't using them in the same way that mechanism wheels are traditionally used. Mechanism wheels are traditionally used on drivetrains to kind of allow robots to drive sideways, but they're not very good on drivetrains. Most people shouldn't be running them on drivetrains, but they work very well if you're trying to get a game object to kind of go sideways while pulling it in. So you have these 45-degree rollers so that as they're spinning on this one axis and they're rotating kind of inwards, they also give some of their force to kind of slide the ball sideways towards the center wheel instead of straight back. So if you just had traction wheels here, the ball would sort of jam up and get caught on maybe this post or the bumper, and it wouldn't kind of force it sideways. These mechanism wheels, because of the way their cones are pointed or these little rollers are pointed, they get a component of their force pushing the ball sideways, and they slide it into the proper slot that they want it in. So they want the ball to be exactly centered on this bar and under this wheel so they can score it kind of in the same location every time. And that's what these mechanism wheels will do on an intake. So a lot of teams have started using them. It became in fashion in 2014 when these 4-inch mechanism wheels started being produced. Vex Pro did it in the first time that season, and it made sense to use it on the big ball in that game. So ever since then, we've had teams using it in pretty much any ball game. Teams have tried to have mechanism intakes in some way. It's not always the answer, but it definitely is a viable solution, especially in single object games where you only have to move one object at a time. Mechanism wheels work really well for that. The second post kind of holds the bottom of the ball. If you didn't have it, the ball would just kind of sit here, and if you went to lift it up, it wouldn't actually go anywhere. So this allows you to pinch the ball between this bar and this omni wheel, so that when you lift it, the ball actually goes up with it. And then looking at the hatch mechanism, so that's these 2 cylinders here and these sort of paddles or fingers, and then they also have these extra cylinders right here that are able to push the hatch out. So during most of the match, these are always retracted. So these would be back in and kind of inside this 2x1. So the hatch, when it touch it, they'd be inside of this. So they'd be in here. I think during the actual event, they had little red balls that they would put on the edge of this, so they wouldn't like scratch the hatch panels or anything with the hard metal here. And so they would go in, these little fingers would go right through the center of the hatch like we saw earlier in their video. They would open them up and grab it so that they would be holding the hatch tightly. And then when they wanted to go put the hatch on the rocket, these would open, and at the same time, these would push out and kind of seal the hatch directly on it. The hatch was all held on with Velcro that season. So having a little bit of force to push it on helped a lot. And then you could also drive the robot sort of into it and make sure it held firmly as well. Okay, and the last thing we'll look at in CAD, we're running close to time, is their level 3 climber. So this was definitely one of the more unique level 3 climbers. There are a couple other teams that had a climber similar. 1817 in Texas, our alliance partners at the Texas district finals, the first Texas district championship, had a climber similar to them. There weren't many teams who had another one like this. And basically, like I said, like we watched that video, we kind of saw it demonstrated, is they built this to be very, very fast. So it took up a lot of their robot geometry. They had to build around it quite a lot in kind of how their frame works and what they're able to do with it. It's powered with 4 775 motors, so they need a lot of mechanical power to be able to lift the entire weight of the robot, right? So they needed to have quite a lot of motors helping drive it. And then you also need a lot of gear reduction because this mechanism doesn't have to spin very quickly, right? It's not rotating very far. The entire climb process goes from the motor here, it starts pushing into the ground, and they're up in the air, you know, at the highest point when it's straight down here. So that's a little, that's less than 180 degrees. And then they finish less than 360 degrees. So the entire motion of this climber is never more than a full rotation of the actual like actuator at the end. So you need a lot of gear reduction. Otherwise, it's going to be trying to spin way too fast, and it's not going to be able to actually lift the robot. So they do that by having a small pinion motor or small pinion gear here driving a larger gear. So they get some reduction. Then they do it again. They have another small gear driving a large gear. Then they do it a third time, having another small gear driving a large gear. And then finally, we have this small sprocket driving this big sprocket. And so they do that twice. they do the same thing mirrored on this other side. So they have all 4 motors going through 2 of these gearboxes, and finally you have a chain reduction. The chain can handle a higher torque a lot of times than the gears. So the gears have these kind of small gear teeth, and it's very possible to chip these or break these teeth off. The sprockets just have more, you have more metal here. There's more actual material. The chain also dissipates some of the what's called shock loads. So you actually will have the chain stretch a little bit and kind of take some of the impact if you go through something where you have too much torque really quickly. And it'll be a little bit harder to break the teeth off or break a chain link, especially when they have the whole thing doubled. So now you have all of the load of lifting the robot running through 2 of these sprockets and 2 sets of chain. So it's very unlikely that you're going to have a failure here when you have everything doubled up as it is. They did also build in this chain tensioner. So this sprocket here isn't driven directly, but they have this built up similar to what they did before on the drivetrain. This bolt is in place. This is actually tapped in here. So as they turn this forward, they're basically able to push on the mounting bolt for this shaft, and they're able to push this sprocket towards the chain. So at the start, this would be backed up pretty close to the end here, and they would push this forward to get the chain into the right tension that they want. The virtual 4-bar aspect of it is what we call a virtual 4-bar chain bar sometimes, is this extra chain here. You can see since this sprocket is actually doing the rotation of the arm. So this main arm is going to be rotated by the gearbox here, and that's what's going to do the lift. But if they didn't have this other chain, this bottom foot wouldn't actually stay, you wouldn't be able to keep this bottom foot and the bottom of the robot parallel, which is what this extra chain does. So this extra chain, since this sprocket here and this sprocket on the inside, this is going to be kind of hard to see. Let me see if I can get it. This sprocket on the inside, since those are the same size, every time that this arms moves a little bit, this sprocket up here basically moves counter to it, or it's going to rotate. It's going to rotate the same way, keeping them everything parallel, which is the point of a virtual 4-bar. So you could imagine if this was not here and this was just fixed, when this was rotated, if this arm got rotated down to the bottom, this whole bottom fork thing would be like off to some weird angle and not flat. So we want to keep it flat. Okay, I think that's most of their robot. There are a few other things they did. What did we not look at? So they had this little curved bit up here is a constant force spring. So this allows the motors on the elevator not have to lift the entire weight of the intakes. Let me see if I can get it in the right spot. So this spring gets attached down to the carriage here. And so it's basically always pulling up on the elevator. It's trying to always lift this carriage up to the top. And it pretty much just balances out the weight of this entire assembly so that when the elevator motors have to move, they're not having to lift all of the weight. They're only just having to fight part of gravity to lift it up a lot less. So your whole mechanism can be a lot faster because the spring is helping you against gravity the whole time and kind of keeping it in a balanced state so that if you lifted part of the elevator and you turned off the motors, it may just be able to sit in the same position because the spring is kind of working against gravity for you already, or if it does fall, it'd fall a lot slower because you have the spring there. Some of the other cool little details, this part right here is a grommet. I think there's a photo of that somewhere. Maybe not. Oh, you can see it in here. So they have wires and tube running into this portion of the elevator. So that lets it go through into the elevator tube without getting cut anywhere, so they can hide some of their wires and tubing inside of there. And it comes out down at the bottom here. Let's let's see, I think we caught most of everything else. They had, they talked about their vision system. This is the Limelight. They had to mount it this direction mostly to be able to not get blocked out by any of the other things happening inside the elevator here. So you have the constant force spring running down. You have the wire for the energy chain coming through here. So this is how they do cable management up to this top bit. This holds all of the hoses and wires and allows those to be nicely run as everything moves up and down. You don't get anything caught or pinched or ripped out or anything. And so they didn't have a lot of room, so this ended up being sideways. But that was okay for them. They also have it kind of at an angle, and that keeps it looking down specifically at the vision targets that they wanted it to, and kind of restrict some of the field of view, which is useful. Let's see, I think that's most everything. Oh, we didn't talk about this upper thing. So the upper sprockets up here are a nice little mechanism. They have, it's a pretty simple process. All it is a bolt that this is riding on, and they have a, let me see if I can hide this nut. They have a bushing on the inside of this. So this is, no, it's actually a bearing. Sorry, they have a bearing directly inside of the sprocket. So this is able to just rotate on this bolt nice and cleanly, and you get a nice smooth rotation of the sprocket using this tiny, tiny bearing in here. Not even sure. Yeah, so it looks like it's somewhat, might even be smaller than 1/2 inch OD. So you have a 1/4 inch inner diameter and a pretty small, it says 0.422. I don't know if that's the actual circle or not. That may just be Onshape being a little weird. Oh, that's actually the flange bit. So I think it's a 3/8 OD if I could get to the backside probably. So you have a really small bearing that's taking, that's running the sprocket here up and down. So it's allowing the sprocket to run smoothly here. Then the actual bearing blocks themselves we didn't look at, but they're nothing too special. They have these machine bearing blocks that are holding the bearings on. So all of the elevator motion moving up and down. So as this part slides up and down, move something I didn't want to. So as this part slides up and down inside of here, they're rolling on the bearings here and here. And they tuck away little tiny ones right in here on the side as well. So you have that bearing there running on this side wall as the elevator moves up and down. And to actually get it that small and in there, they had to cut out part of the tube here. So they had to do some work to make sure they fit everything. So you can start seeing it where the details come into these robots. You get a lot of really, really tiny details that are really important. Like if you designed all this, but then didn't cut this little part out, this whole mechanism doesn't work. So they had to make sure they got all the details right there to get those bearing blocks working the way they wanted to. And then the carriage assemblies are similar. They just built them together into like a big flat plate. So this whole plate here gets milled out, and it holds the it holds all sets of bearings. So it has the bearings at the top and bottom here. You have the top and bottom on the back. And then you also have these 4 side bearings that run the entire carriage up. And then they're bolted together by these 2x1s that cross the whole thing to make the carriage. Let's see if I can force that transparent. Yes, you have this block in here that's able to hold those together. So these bolts here get bolted into this block, and then the outer 2x1 extrusion gets bolted into that. And that's what's holding that whole carriage assembly together. So they can move everything up and down. They did have to package their battery pretty interestingly, right? It had to be right at the very front here. There's partially because of weight probably, but also just because they were running out of room in the back here. Even to the point where they had to, let me see if there's a photo of it. Yeah, so the battery connector had to actually come in kind of into this ball space. So when this comes down, their battery connector is like wrapped around where this intake is. Which is definitely a little scary, but I don't think it was ever a problem for them. That's inside the frame perimeter and everything, right? Because this is where their bumpers are. So nothing too crazy there. Okay, I think that's gonna wrap up our look at their robot.